Okay, so what we're going to be talking about today is effectively what happens when our tail current isn't provided by an ideal source. Okay, and then we're going to mess around with that slightly. Okay, so I'm going to call this common mode rejection. So some of you may, while looking through data sheets on amplifiers for your various projects and all of this kind of stuff, may have come across a figure of merit called the common mode rejection ratio on these data sheets. And what we're going to be talking about today is effectively where that comes from and what it means. Okay. So we're going to consider a circuit. We're going to deal with a MOSFET here just for the sake of argument, but it doesn't particularly matter. Where we have some resistance RD, like so. Here's V out 1. Here's transistor M1. Here's transistor M2. Here's another RD. Voltage V out 2. And what I'm going to do here is, instead of just having my ideal tail current source here, which would be some current ISS, I'm going to put that tail current in parallel with some resistance RSS, so that we're effectively placing a practical current source as our tail current as opposed to our ideal current source. Well, this practical current source is representative of just simply a transistor-based current source, right? Because we know that it will have, it'll drive some amount of current flowing down through the tail of the differential pair, and it will have some associated small signal resistance as well, okay? And what we're going to look at is what happens when we apply a common mode signal to this configuration. So I'm going to have some signal here, VCM, that's applied to transistor M1, or at the gate of M1, and I'm also going to apply that exact same signal to the gate of transistor M2. And I want us to pay attention the voltage at this node that I've labeled X. Okay? So we're going to talk things through here qualitatively to kind of figure out what's going on. So anytime that we're applying a common mode signal to our input terminals, we should see that there is a current ID1 and a current ID2 flowing through our transistors. For a common mode signal, ID1 and ID2 should be perfectly matched. They should be literally the exact same thing, right? Now, when we have this practical current source here at the bottom, applying a common mode signal messes things up ever so slightly. And what I mean by that is, if we apply a common mode signal, the voltage at node X is going to move, right? So depending on how large of the common mode signal we apply, our voltage at X is going to move up or down. Well, because our tail current source now has a resistance, that means that depending on what the value of X is, so if X were 0, no current is going to flow through RSS. But if we apply a large common mode signal that brings that nodal voltage X up, now RSS is going to start leaching current away from our current source, right? Which means that while ID1 and ID2 are still going to be equal, they're going to be less than they were before, which means the voltage at our output nodes is going to be different than what it was when that resistor wasn't there, right? So we are going to experience some amount of common mode gain, right? So the difference between our output voltages is still going to be zero, but we're going to see some amount of response due to our changing input signal, okay? So in order to quantify this, we are going to look at our circuit effectively as an amplifier. So before we move into redrawing this thing here, though, I want us to understand that since Vout1 and Vout2 will always be the same voltage because they ID1 and ID2 will always be the same current in a perfectly matched system, I'm going to short circuit those two nodes because the potential difference between them can never not be zero. Are we okay with that? So if Vout1 and Vout2 was always the same voltage, there's nothing remotely wrong with me just connecting them by a wire. So when I do that, what I'm going to see is something that looks like this, okay? So here's my supply voltage, VDD. What's going to happen to those resistances RD? They're exactly in parallel, so I'm going to replace them with a single resistance that is just RD over 2. Absolutely right. Here's transistor M1. I'm going to put transistor M2 over here. And I am just tying these gates together. So this is just a shorthand notation for me applying the same voltage at the gates of both. And here's our signal VCM. And here's our output voltage node. Here's ISS. And here is RSS. So if we were to look at this as an amplifier, what do you guys think it looks like? So our input signal, VCM, is applied at our gate. Are we in agreement with that? Our output signal, Vout, is taken at the drain. So what kind of amplifier is it when we have our input signal applied at the gate and our output signal taken at the drain? Common source amplifier, absolutely right. Now, this common source amplifier, it has some load resistance, RD over 2, so that checks out pretty well. What's RSS doing? Exactly right. It's serving as a degeneration resistor for our small signal analysis. So this is nothing more, effectively, than a common source amplifier experiencing source degeneration, right? From a small signal perspective. Because we know what that entails, we don't actually need to analyze this at all. We already know how this thing behaves, right? So we can call our common mode gain AV CM. So this is going to be defined to be the change in our common mode output voltage divided by the change in our common mode, input voltage as nothing more than the gain of a common source amplifier undergoing degeneration. So with channel length modulation neglected, because I didn't have time to update my notes for this, that's going to look like RD over 2 divided by RSS plus 1 over twice GM. And that can be rewritten as negative GMRD divided by 1 plus twice GM RSS for a MOSFET-based differential pair amplifier, and it's going to be negative RC over 2 divided by REE plus 1 over twice GM, which can be written as negative GM RC divided by 1 plus twice GM REE for a BJT-based differential pair amplifier. Again, channel length modulation is being neglected here, or early effect is being neglected here, just because it makes this look really, really gross, really, really quickly. So what do you think the value of this common mode gain is generally going to look like based on these expressions? So let's think about things here, okay, right? RSS and REE by extension are the output resistance of a transistor-based current source stage. So if we had a single transistor acting as a current source, that would look like R0, right? If we had a cascaded current source, that would be significantly higher than R0, okay? So we're going to have 1 plus twice GM times some large resistance to some incredibly large resistance in our denominator. And in the numerator, we have GM times either RD or RC. Well, typically speaking, RD or RC is going to be much less than that resistance R0, and definitely significantly less than that resistance of a cascaded current source, right? So our differential mode, or excuse me, our common mode gain here is going to be quite small. Okay? Typically significantly less than 1. Okay? It's still happening, but it's usually so small that in the overwhelming majority of cases, we can neglect it because it doesn't really contribute a whole hell of a lot. Okay? However, it's only neglectable or negligible if our system is perfectly matched, meaning that our two resistors RD are the same and our two transistors M1 and M2 are the same. If either of those things are not matched perfectly, we're going to wind up having what's called a common mode to differential mode conversion gain, where a common mode signal is actually going to influence the behavior of the output significantly. And we're going to look at what both of those cases entail. So let's start by looking at resistor mismatch. So starting with our basic circuit, let's say on this side we have some resistance RD. Here's transistor M1, V out 1. And then here we have a resistance of RD plus delta RD. Here's V out 2. Transistor M2. And I did not give myself enough room. Tie these guys together. And I'll just stick it down here for lack of a better place to put it. Here's our tail current, ISS, and our tail resistance, RSS. So if VCM increases by a small amount that we're going to call delta VNCM, then ID1 and ID2 change, or actually, let me put this explicitly, increase by a factor of GM divided by 1 plus twice GM RSS times delta VNCM. So that's how much our drain currents are going to change by. However, because RD1 and RD2 are not the same, V out 1 and V out 2 don't change by the exact same amount. Okay. So the change in V out 1 is going to be negative delta VNCM times GM over 1 plus twice GM RSS times RD. And the change in V out 2 is going to be negative delta VNCM GM over 1 plus twice GM RSS times RD plus delta RD. And therefore, our change in our output voltage, which is just delta V out 1 minus delta V out 2, is going to be negative delta VNCM GM over 1 plus twice GM RSS times the change in our resistance. So we can see that a change in the common mode input voltage produces a change in the differential mode output voltage. So we have what's called a common mode to differential mode conversion gain. We're going to call AV CM dash DM. Okay, so common mode to differential mode conversion gain. And this common mode to differential mode conversion gain is defined as the change in our differential mode output voltage caused by a change in our common mode input voltage. And from above, we can see that this is simply going to be GM times delta RD over 1 plus twice GM RSS, which is approximately delta RD over twice RSS for MOSFETs. And it's going to look like GM delta RC over 1 plus twice GM REE, or approximately delta RC over twice REE, or sorry, I put BJTs when beta is large. Realistically, beta being large just means 10 or higher. Yes, ma'am. So not quite. So the transistors are mapped in as much as they have the same early voltage, they're the same size, all of those appropriate. So if it's a MOSFET, they have the exact same aspect ratio. They're both NMOSs, all of that kind of good stuff. So K N in this case is going to be identical for both of them, but they're going to be carrying slightly different currents because they see slightly different resistances. And that's where that change in our output voltage stems from, right? So the DC operating point of our output voltage won't be exactly where we think it should be because we are seeing our common mode signal is pushing one of our outputs a little bit away from the other one. So this common mode to differential mode conversion gain is bad, but it's hard to understand how bad it really is without putting it in context of our common mode gain as well. And so what I mean by that specifically is that if our circuit has a very large differential mode voltage gain and a very small differential mode to, or excuse me, common mode to differential mode voltage gain, it's not really going to make that big of a deal. And so we quantify this by what's called the common mode rejection ratio. So common mode rejection ratio or CMRR, and this is the figure of merit that you'll see on your data sheets, is 20 log, goodness, I can't write to save my life today, our differential mode gain, so AVDM, let me write that better, divided by our common mode to differential mode voltage gain. And sorry, this should be an absolute value thing. So the ratio of the differential mode gain to the common mode to differential mode conversion gain really tells us whether or not this is going to be a thing. Okay. So if we were to pull up the data sheet, which I can do, for an op amp that's based on BJT technology, just because I happen to have that already saved here. Or I thought I did. There we go. Common mode rejection ratio right here. So it's typically in the ballpark of 90 decibels for a TI UA 741 op amp based on BJT technology, right? What does 90 decibels mean again? Like in a linear scale? So because it's 20 blah, blah, blah. So 20 dB means that it's 10 times larger. So 40 dB is it's 100 times larger. 60 dB would be 1,000 times larger. 80 dB would be 10,000 times larger. So this is going to be, I think, in the ballpark of 70,000 times larger. So our differential mode voltage gain is about 70,000 times larger than our common mode to differential mode conversion gain for this particular op amp, right? So circuits can definitely be designed to provide a high amount of common mode rejection ratio, okay? Realistically, anything over 60 dB is fantastic. You're not really going to have to worry about things too terribly much. So it's just something to kind of keep in the back of your head. There are always going to be manufacturing tolerance issues and all of that kind of stuff with any integrated circuit that you ever design, purchase, and all that kind of jazz. So having some understanding of what the common mode rejection ratio is will tell you how much those imperfections are going to influence the overall behavior of your system. Okay. So that's what happens when we have a transistor, or excuse me, a resistor mismatch. Now let's talk about what happens when our transistors aren't exactly the same. So we've got our circuit. This time the RDs will be identical. Here's V out 1. Here's V out 2. Here's transistor M1. Here's transistor M2. Tie these guys together. tie our gates together. So we have some common mode input signal, and then we have our two output signals. And now let's say that the aspect ratio of transistor 1 does not equal to, the aspect ratio of transistor 2. So everything else is the same, but our aspect ratios are slightly off, okay? What small signal parameter do you think that this is going to impact? Our transconductance GM, absolutely right. So this is going to make GM1 not equal to GM2. So we should observe that our differential output is going to see some corruption or distortion, okay? All right, so for a small change in VCM, which we're going to call, once again, delta VN CM, the voltage at node X is going to simply be RSS times IX. So this is small signal, what we're looking at here. And that's going to be GM1 times delta VNCM minus VX plus GM2 delta VNCM minus VX times RSS, which could be expressed as GM1 plus GM2 delta VNCM minus VX RSS. Our change in our output voltages, we're going to have negative GM1 times delta VN CM minus VX times RD, which can be written as negative GM1 RD over 1 plus GM1 plus GM2 RSS times the change in VNCM. And delta V out 2 is going to be something similar. Negative GM2 delta VNCM minus VX times RD. Oops. Or negative GM2 RD over 1 plus GM1 plus GM2 times RSS times delta VN CM. And our change in our differential mode output voltage is then going to be negative GM1 minus GM2 times RD over 1 plus GM1 plus GM2 RSS delta VN CM, which yields a common mode to differential mode conversion gain of negative GM1 minus GM2 RD over 1 plus GM1 plus GM2 times RSS. And obviously, the more our transistor aspect ratios are different from each other, the larger this common mode to differential mode conversion gain is going to be. Because I couldn't find my notes for single stage op amps because I was in a hurry to get over here, we are done for today. Yes.
Go back up where
Common mode rejection ratio thing? Yeah. So it's just the ratio of the differential mode gain to the common mode to differential mode conversion gain expressed in decibels. Just the ratio of the gains. All right, so I put 2 homework sets up over the weekend. I'm going to be putting the first design project up, I think here within the next hour or so. Oh, I definitely do. I definitely do. It's going to give you guys some experience with I hesitate to call it a program because it's really not a program. It's just a Java file called electric VLSI, where electric VLSI is a tool that you can use to literally design integrated circuits. So your first design project is going to be to design I'm going to call it simple. It's not particularly difficult amplifier. I think if I remember correctly, it is a common source amplifier. All of the capacitor sizes and all of that kind of stuff are going to be given to you. You just need to find the resistor values based on the design criterion and all of that kind of good stuff. We are going to use the results of your design projects, which there's actually only one solution, so I don't know how much of a design project it actually is. But we're going to use the results of your design project to facilitate our jumping off point for when we're looking at the frequency response of circuits. So you guys putting in the correct capacitor sizes, which again are given to you and all of that kind of good stuff is going to influence the frequency response of this thing. And then we're going to talk about why it behaves the way it does. So it's relatively important that you get it done in a timely-ish fashion, but as long as somebody has it done, and I already have it done, I can just throw up the simulation and show you what we're dealing with. So, yes. I'm hoping to have the exam posted for Friday. So I have a couple of homework problems for the material that we covered today that I want to give you guys because I want to put a question on the test about it. But realistically, the test is just going to be effectively I take a problem or two from each homework set, change the numbers, and then have you guys go at it. Or I might change a circuit slightly or whatever. So like one that I have in my head that I'm 99% sure I'm going to give you is one that looks like a cascode amplifier, except that the cascode is formed with an NPN BJT as well as a PNP BJT, which means it doesn't actually behave like a cascode. And so I would want you to use the short circuit transconductance method to determine the voltage gain of that system. So if you can find the short circuit transconductance and then the output resistance, you're good to go. So it's applying what we learned to a circuit that doesn't quite meet the criterion of I can literally just regurgitate the equation I gave to you. Hannah. if you were trying to derive the relationships and stuff like that, then yes, the short circuit transconductance method is typically going to be easier to do than a more direct analysis method. If you're asking about what I am expecting you guys to do for this homework set, it is largely to use your notes and say, I know how this part works, so here's the equation that I should use, and go from there. So I did give you a problem explicitly to make you practice using the short circuit transconductance method. I am not trying to dissuade you from using that method to come up with your own relationships for the voltage gain and this, that, and the other. I'm saying my expectation is that you take the notes and information that have been provided to you and just use that as a jumping off point, as opposed to doing all of it yourself.
But if they were to, like, going through read like for number two, what would you want to do?
So let's look at number two, because I don't know what number two is off the top of my head, because I have slept since yesterday. Open, you bastard. Stop trying to rename the folder. Oh my God. Oh God, how did I get to senior design? So for problem two, explicitly, I'm not, again, not trying to dissuade you from using the short circuit transconductance method or anything like that, but I don't think it's necessary. And let me explain what I mean specifically. Okay. So if we were to short circuit our output node, all of that business up top does not contribute literally anything to our circuit whatsoever. Because one side of this resistance is at ground up here and the other side is at ground on the bottom. So it doesn't do anything. I am 97% sure that I already did the short circuit transconductance analysis of that for you. So you're welcome to do it again if you were so inclined, but I firmly believe it is entirely unnecessary. So if my memory serves me correctly, the short circuit transconductance of this guy is literally just going to be the transconductance of Q1. So what I am expecting you to do is acknowledge that our short circuit transconductance is just GM1. And then from there, you can find the resistance down and the resistance up. Put those two in parallel, multiply it by GM, and call it a day. The resistance down, I have also done for you. The resistance up, I haven't. So that's the only part where you actually need to apply things. But realistically, you've already done something like that before, because that's just this guy right here being degenerated by a diode connected transistor. So you could just replace, as a NPN, because it literally doesn't matter, what you're looking at is this resistance. Here's Q3. Because this is diode connected, if memory serves me correctly, this will be R pi in parallel with R naught in parallel with 1 over GM, and all of these should have a 4 associated with it. So if you have in your notes somewhere where you have a transistor degenerated by resistance, replace the resistance with that and call it a day. Not saying not to derive it if that's the way that you want to do it. Saying that's not my expectation.
So the G, you know, parts A and B should go to these. Start that way.
Yes. Yeah, so the short circuit transconductance for this circuit is going to be identical regardless of whether Q4 is diode connected or Q4 is connected like a current source. Will not impact anything because everything looking up from the output node is just a small signal resistance. And when we short the output node, that resistance is between ground on top and ground on bottom, so it contributes nothing to our short circuit transconductance calculation. Yes. For problem 3, kind of the same thing, except it's a MOSFET. So now the short circuit transconductance is once again just going to be the GM of transistor M1. The resistance looking down is going to be the resistance of a cascode current source. The resistance looking up for part A is just going to be the resistance of a transistor current source. And for part B, the resistance looking up is the resistance of a cascode current source. So all of the parts are stuff that we covered in class. You're just putting it together. Okay, good. So for what it's worth, oh, I thought I plugged my laptop in, but whatever. I don't expect the lecture on Wednesday to take more than 30 minutes to 45 minutes at the absolute max. So there should be time for you guys to ask questions about homework problems and all that kind of stuff after you've had an opportunity to look at them and all that kind of jazz in class on Wednesday. Friday, my goal is to have the test up, and then I will be here to just answer questions that you guys have about homework assignments, tests, and all that kind of stuff. And then we're not going to cover anything new until Monday when we start our frequency domain stuff. So that's what I have planned for this week. If you guys want it to be something different, I'm open to suggestions, but that's what I want to do. So, what up? Yes, ma'am.
What exactly is like point of going
I don't fully understand your question. So what we did today, you're asking about?
Yes, but also more like also just generally.
Okay, so why we analyze a differential amplifier at all is because it is a fundamental building block of integrated circuit design. It is one of the biggest parts of an op-amp, which realistically, let's see if I can pull that back up really quickly. This is an aside type thing here. So this is our functional block diagram of this op-amp. This part right here, actually, is effectively what we're going to be talking about on Wednesday. Okay. Now, let me undo this slightly. This part right here is just a differential pair amplifier, except that it has a current mirror as a load. Now it looks a little odd because this is a PNP differential pair, and we've derived everything using NPN differential pairs. But we can see that our transistors, so I could call this guy right here. So here's Q1 where our non-inverting input is applied. Here's Q2 where our inverting input is applied. This bit right down here is literally just a current mirror. This bit right here is our tail current source. Just for what it's worth, this bit right here is another current mirror, except that each one of those transistors is degenerated by a resistor to give it a larger output resistance. This transistor right here is that, I guess this would be an emitter follower transistor, much like we did with our current mirrors, that's supplying our base currents and all of that kind of stuff to minimize our copy error. What do we have right here? I'll be damned, it's another current mirror. Let's see. Effectively everything to the right of this line is what's called a push-pull output stage, which we might get to talk about in this class, but if we don't, and you give a shit, we'll talk about it in integrated circuits. Let's see, taking my output. This network right here that I just circled is for frequency compensation. That's something that we'll be talking about a little bit later. This part right here is just a secondary gain stage, which I thought this just used a common emitter amplifier, but I might be mistaken. But anyway, all we're doing, the point of this entire class realistically is to just have an understanding of how all of these fundamental building blocks works, so that if you choose to take integrated circuits, you know what Legos you have available in order to build a functional amplifier. Okay. Now, what we did today explicitly was we were figuring out what happens when we don't have the ideal case, right? So what happens when we are making a real op-amp, as it were, and our transistors aren't perfectly matched because some misalignment happened in our fabrication process, either misalignment in the size of the resistors or misalignment in the size of the transistors, and how that manifests in affecting the overall voltages. Did that maybe kind of clarify what the hell we're doing?
Are used a lot like this.
So, yes, in as much as any input signal that we apply to both of the input terminals doesn't show up in the output of the system. Yes, 100% yes. But a differential pair is used anytime we have multiple input signals and we want to do something with multiple input signals, right? So the op-amp here, again, nothing more than just a fancy, complicated transistor circuit built of smaller circuits that we've been dealing with in this class, is designed in order to do mathematical manipulation of multiple inputs, right? And we talk about some of that in circuits too. We can add signals together. We can take the differences. We can integrate signals. We can differentiate signals, all of that kind of stuff. All of that stemming from the fact that we have a differential pair as our input stage of our amplifier. Because if we had a single-ended input, we could only do stuff to one signal, which means our options are limited to making it larger or making it smaller. End of story. As we can accommodate more than one input, we can do much more mathematical manipulation of those signals. So a consequence of a differential pair is that noise reduction occurs if we apply the noise equally to both inputs. But the true purpose of a differential pair is to be able to manipulate multiple input signals. So the common mode is effectively just us describing what happens when we put the same signal on both of the inputs. That is by definition a common mode signal. If the same signal is applied to both of the inputs, it is common to everything. If different signals are applied to the inputs, then we have a differential mode signal. And we can decompose literally any signal that we apply as this part is differential mode, this part is common, right? So if I had one signal is this, right? I'm applying all of my signal to input one and no signal whatsoever to input two. My common mode signal is literally just VN1 plus VN2 over 2. It's just the average. And then my differential mode signal is VN1 minus VN2. And so that we can decompose or redraw this effectively as the signal applied to VN1 is some portion of my common mode signal, or really all of my common mode signal and some portion of my differential mode signal. And the thing that's applied to VN2 is all of my common mode signal and some portion of my differential mode signal. Because the op amp or the transistor circuit itself really doesn't care what's applied where. It just depends. It just cares which portion is the common mode and which portion is the differential. Yes. Push it out. Yeah. I'm going to try to get the test posted before Friday, but I'm not going to make it due until the 19th regardless. Because you guys got other assignments from me and all that kind of stuff to worry about too. And I'm going to try is the imperative word here, a better job of posting homeworks around the exact same time that we covered the material, not, I don't know, 2 weeks later like a jackass because I got busy and forgot. So again, keyword is try, but yeah. Anything else? All righty, see you guys on Wednesday.